5 signals. That's what the team reported. 5 narrow, upward-sweeping radio signals detected in the central beam of the world's largest single-aperture radio telescope while it was pointed directly at an object from interstellar space. Not in the side beams, not in background scans, only in the main observational path. At first glance, that detail alone is what makes the observation unusual. Radio telescopes don't just listen to one direction, they compare multiple beams to filter out local interference. So when a signal appears only in the central beam, it immediately raises a question. Is it coming from the target, or is it somehow tied to the instrument itself? The researchers who analyzed the data concluded that the signals were consistent with clock oscillator intermodulation, internal electronic artifacts generated by the telescope's own timing hardware. In simple terms, the telescope's internal clock operates at fixed frequencies, and those frequencies can produce harmonics that sometimes appear in the data as false signals. If a detected frequency matches one of those harmonics, it can be classified as instrumental noise rather than an external transmission. But that explanation, while standard in radio astronomy, depends on multiple conditions being satisfied. It assumes the interference is not directional in origin, that it appears consistently across observations, and that it is not tied to a specific target or pointing configuration. This is where the case becomes interesting. The signals were detected on a specific date, January 5, 2026, during a campaign targeting an interstellar object known as 3I, Atlas. Observations were conducted across multiple dates, including earlier sessions in October and additional scans in December. Across those earlier observations, no comparable signals were reported. The 5 chirp-like signals only appeared during this final observation window. To understand why that matters, it's important to understand what a chirp signal is in radio astronomy. A chirp refers to a signal whose frequency increases or decreases over time in a continuous sweep. Such patterns are often associated with engineered transmissions or systems designed to maintain signal integrity across changing conditions. Natural astrophysical sources tend to produce broadband emissions rather than narrow, structured sweeps. The signals in question were narrowband and exhibited chirp-like characteristics. That combination, narrow frequency content plus time-based frequency variation, is precisely what distinguishes artificial signals from most natural noise sources. However, classification alone doesn't determine origin. The telescope team attributed the signals to internal clock-related effects because the frequencies aligned with known harmonic intervals of the instrument's timing systems. In radio instrumentation, this is a known phenomenon. Internal oscillators can introduce spurious tones that mimic external signals if they coincide with observational frequencies. Still, there are unresolved aspects that make this explanation incomplete in the strictest sense. Clock-generated interference typically does not depend on where the telescope is pointed. It arises from the hardware itself and should, in principle, be detectable across multiple observations and beam positions if the same system conditions are present. In this case, the signals were confined to the central beam and only appeared during a single observation period directed at a specific target. That raises a geometric and temporal question. Why would internally generated harmonics manifest in a way that appears directionally tied to one object and one observation window, while not appearing in others conducted under similar operational conditions? This doesn't invalidate the instrumental explanation, but it does highlight that the classification relies on frequency matching rather than directional behavior alone. In other words, matching a known harmonic is sufficient to flag a signal as likely instrumental, but it doesn't fully address why the signal appeared in that particular observational configuration. At this stage, the data was logged, categorized, and the case was effectively closed from an observational standpoint. No follow-up detections of similar signals have been publicly reported. No additional anomalous patterns have been confirmed in subsequent observations. And so, the interpretation stands: instrumental noise consistent with internal oscillator harmonics. But the observation itself, 5 narrow chirp signals appearing in a single beam pointed at an interstellar object, remains an unusual data point in a broader campaign that was designed to detect exactly this kind of phenomenon. To understand the full context, we need to step back from the signals themselves and look at how this object was observed across multiple missions, instruments, and timelines. That broader data set is where the next layer of complexity emerges. The radio observations were only one piece of a much larger observational effort. Around the same period, multiple space-based and ground-based instruments were independently tasked with studying 3I Atlas from different vantage points and using different measurement techniques. One of the most significant contributors was ESA's JUICE spacecraft, which was already en route to Jupiter. During late 2025, JUICE was positioned in a unique geometry relative to the object close enough to conduct detailed observations during and after its perihelion passage. This created an opportunity to gather high-resolution scientific data from instruments designed specifically to analyze icy bodies and comet-like objects. JUICE conducted multiple observation sessions between early November and late November 2025. Across these sessions, the spacecraft used 5 separate scientific instruments, each operating in a different observational regime. Together, these instruments produced over 100 individual data files, totaling more than 11 gigabytes of raw scientific information. However, what was publicly released from this campaign was limited. The primary public-facing material consisted of navigation camera footage compiled into a short video showing a bright object with a trailing tail moving against a star field. This visual presentation aligned with what one would expect from a comet-like body undergoing solar heating. The disparity between the volume of collected data and the limited nature of the publicly released material is not unusual in space missions. Raw scientific data requires calibration, validation, and interpretation before being made widely accessible. In many cases, only selected summaries or visual representations are shared initially. Still, the timing and structure of the JUICE campaign are notable. The observation window was organized rapidly after the confirmation of 3I Atlas, compressing what would normally be a long planning cycle into a much shorter time frame. This required coordination between mission operations teams and instrument specialists to ensure that observations could be executed within the available opportunity. In parallel, another important dataset came from NASA's Transiting Exoplanet Survey satellite, known as TESS. TESS continuously scans large portions of the sky, primarily searching for exoplanets by detecting dips in stellar brightness. However, its wide-field observational capabilities also make it capable of recording transient objects passing through its field of view. After the official announcement of 3I Atlas in July 2025, researchers identified earlier test data showing that the object had been captured in May 2025, several weeks before its formal discovery. This retrospective identification is consistent with how archival astronomical data is often used. Once an object is known, scientists search existing datasets to extend its observational history. The presence of pre-discovery data does not imply that the object went unnoticed at the time. Rather, it reflects the nature of automated survey pipelines, which process vast quantities of data continuously. Objects that do not immediately trigger classification thresholds may only be recognized later when targeted searches are performed with updated parameters. In this case, the test data contributed to refining the object's trajectory and improving orbital models. By extending the observational baseline backward in time, astronomers can reduce uncertainties in predicting future positions and behavior. Taken together, The JUICE observations, TESS archival detections, and other survey data formed a multi-instrument dataset spanning different time periods, wavelengths, and observational geometries. Each dataset contributed a different perspective on the object's physical properties and motion. What emerges from this combined effort is not a single anomalous measurement, but a collection of observations that are being interpreted within the framework of known cometary physics. Variations in brightness, spectral characteristics, and outgassing behavior are compared against established models derived from decades of comet observations. In that context, the object is treated as an interstellar comet, an icy body originating outside the solar system, passing through and interacting with solar radiation in ways that produce observable tails, comae, and volatile emissions. However, as we move deeper into the data from these instruments, additional measurements begin to reveal properties that differ from typical cometary expectations. These differences don't necessarily contradict the comet classification, but they introduce parameters that require careful interpretation. The next part focuses on those physical and chemical observations, measurements that probe the composition of the object itself rather than its motion or radio emissions, and how they compare to what scientists expect from known comet populations. Beyond imaging and trajectory tracking, one of the most important aspects of studying an interstellar object is understanding its composition. This is where spectroscopic and particle-based instruments come into play, allowing scientists to analyze the materials being released from the object as it interacts with solar radiation. Multiple observatories contributed to this effort, including space telescopes and planetary missions equipped with instruments capable of measuring volatile compounds such as water vapor, carbon dioxide, and carbon monoxide. These gases are typically released when a comet approaches the Sun and its surface warms, causing sublimation of ices embedded within its nucleus. By measuring the relative production rates of these volatiles, scientists can infer the chemical makeup of the object's interior. In well-studied comets, these ratios tend to fall within known ranges that reflect the conditions under which the comet originally formed in the early solar system. For 3I, Atlas, the reported measurements indicated that its volatile production ratios differed from what is typically observed in solar system comets. While the exact interpretation of these differences requires detailed modeling, the key point is that the object's chemical emissions did not align perfectly with established baseline profiles. In addition to volatile gases, spectroscopic observations detected elevated levels of certain metallic elements in the surrounding coma, particularly nickel. In most natural comets, elements like nickel and iron appear together in proportions consistent with cosmic abundances, with iron typically being more dominant. In this case, the observed nickel-to-iron ratio appeared unusual, with nickel present at levels that did not follow the standard pattern. Such deviations can occur due to a variety of factors, including surface composition differences, selective release processes, or observational uncertainties. However, the presence of metals in a comet's coma is not unexpected. As solar radiation heats the nucleus, it can liberate dust and embedded materials, exposing and dispersing elements that were previously trapped within the object's structure. The distribution and ratios of these elements provide clues about the object's formation history and subsequent evolution. Another important factor is isotopic composition. Measurements of isotopic ratios can help determine the environment in which an object formed. For interstellar objects, these signatures may reflect conditions in distant star systems with different metallicities and chemical abundances than our own. In the case of 3I, Atlas, isotopic data suggested formation in a low metallicity environment consistent with regions of the galaxy that contain fewer heavy elements. This aligns with theoretical expectations for objects formed around older or less metal-rich stellar populations. However, interpreting these results requires caution. Differences in measured ratios do not necessarily imply non-natural origins. Cometary bodies can exhibit a wide range of compositions depending on their formation, zone, thermal history, and subsequent exposure to radiation over billions of years in interstellar space. What makes interstellar objects particularly valuable scientifically is precisely this diversity. Unlike solar system comets, which formed under relatively similar conditions, interstellar objects originate from entirely different stellar environments, potentially preserving chemical signatures from regions far beyond our observational reach. As a result, deviations from familiar cometary patterns are not inherently unexpected. They may simply reflect the broader diversity of planetary formation processes across the galaxy. Still, when multiple measurements, volatile ratios, elemental abundances, and isotopic signatures are considered together, they form a composite picture that researchers must interpret within the limits of current models. Any inconsistencies or anomalies are typically flagged for further study, comparison with additional datasets, and peer-reviewed analysis. In the next section, we move from chemical composition to spatial distribution, how the materials are arranged within the coma, and what that can reveal about the internal structure and behavior of the object itself. One of the most informative tools in spacecraft instrumentation is spatially resolved spectroscopy, measuring not just what substances are present, but where they are located relative to the object's nucleus and how they are distributed across the surrounding coma. The MAGUS instrument aboard JUICE is designed specifically for this purpose. Rather than capturing simple images, it records spectral data across a range of wavelengths, effectively mapping the chemical composition of the observed scene pixel by pixel. This allows scientists to build a spatially resolved profile of molecular and elemental distribution. When applied to a comet, this type of instrument can distinguish between materials originating directly from the nucleus and those formed through secondary processes in the coma. For example, certain molecules may be released in localized jets, while others may be distributed more evenly due to sublimation across the surface. If a comet is behaving in a typical manner, one would expect the composition of its coma to show gradients or patterns corresponding to active regions on the nucleus. These regions can vary based on surface features, rotation, and exposure to sunlight. Uniform distribution, on the other hand, may suggest more homogeneous outgassing or a lack of strongly localized activity. Either outcome can be consistent with natural processes, depending on the physical characteristics of the object. In the case of 3I, Atlas, MAGUS data was collected across multiple observation windows during November 2025. These datasets, combined with other instruments, provide a multidimensional view of the object's chemical and physical behavior during a critical phase of its solar encounter. Another instrument, the Particle Environment Package, PEP, measures charged particles such as ions and electrons surrounding the spacecraft and its target. This allows researchers to assess the plasma environment around the object, including any interactions between solar wind and material emitted from the comet. Comets often interact with the solar wind, creating structures such as ion tails that are shaped by electromagnetic forces. These interactions are well understood and follow predictable patterns based on known physical laws. Deviations from these patterns can indicate variations in outgassing rates, magnetic interactions, or environmental conditions. The Sub-Millimeter Wave Instrument, SWI, provides additional insights into temperature-dependent molecular emissions. By observing at sub-millimeter wavelengths, it can detect rotational transitions of molecules that are otherwise difficult to observe, offering a complementary perspective on the chemical composition and thermal state of the object. Meanwhile, the ultraviolet spectrograph, UVS, focuses on high-energy interactions, including photodissociation processes where solar radiation breaks molecular bonds. The resulting emission signatures, help determine the stability and structure of different compounds within the coma. Each of these instruments contributes a different layer of information. MAGIS maps spatial distribution, UVS tracks molecular breakdown, SWI probes thermal and molecular structure, and PEP examines the particle environment. Together, they form a comprehensive observational suite designed to characterize the object from multiple physical perspectives. What remains consistent across these measurements is that the data requires careful calibration and interpretation. Instrument sensitivity, observational geometry, and environmental conditions all influence the resulting datasets. At this stage, no single measurement defines the object. Instead, scientists compare all available data against established models of cometary behavior, looking for consistencies and discrepancies that can refine their understanding. In the next section, we return to the timeline of observations and institutional responses, focusing on how different agencies coordinated their campaigns and how the scientific process handles emerging data of this kind. Large-scale scientific investigations like this one involve coordination across multiple agencies, institutions, and research teams. Once an object like 3I, Atlas, is identified, observation campaigns are rapidly organized to maximize the scientific return during the limited time the object is accessible. Space agencies such as NASA and ESA, along with ground-based observatories and independent research programs, each contribute observations using their own instruments and methodologies. These efforts are often complementary, covering different wavelengths, time windows, and observational angles. In the case of 3I, Atlas, the JUICE campaign represented one such coordinated effort, leveraging a spacecraft already in transit to Jupiter to obtain data that would not otherwise be possible from Earth-based telescopes alone. At the same time, radio observations, spectroscopic measurements, and archival searches were conducted independently by various teams. Each dataset was analyzed according to established scientific protocols, including validation, calibration, and peer review where applicable. When multiple datasets converge on similar conclusions, confidence in those conclusions increases. When discrepancies arise, they become the subject of further investigation, additional modeling, or follow-up observations if the object remains accessible. In this instance, some observations reported differences from typical cometary expectations in areas such as volatile production rates and elemental ratios. These differences are not unprecedented in interstellar objects, but they do provide opportunities to refine models of how such bodies form and evolve. The detection of radio signals in a separate observational campaign added another layer of data, though the signals were ultimately attributed to instrumental effects. Radio telescopes are highly sensitive to both external and internal sources of interference, and distinguishing between the two is a fundamental part of radio astronomy. The classification of those signals as clock-related artifacts reflects a standard methodological approach. When a signal matches known internal harmonic frequencies and lacks corroborating evidence across multiple beams or observation sessions, it is typically attributed to instrumentation rather than an external source. At the same time, scientific conclusions are always based on the best available evidence at the time. As new data becomes available, interpretations can be revisited, refined, or confirmed through additional analysis. It is also important to recognize the role of archival data in astronomy. Observations are often stored and later reanalyzed as new objects are discovered. This allows researchers to extend the observational history of an object backward in time, improving orbital models and providing additional context for its behavior. The identification of earlier detections of 3I, Atlas in test data is an example of this process. Once the object was recognized, researchers were able to locate prior observations that had captured it without immediate classification. Throughout this process, communication between agencies and the public follows established protocols. Preliminary findings are often shared in summarized form, while detailed analyses are published later in scientific papers or reports. This ensures that conclusions are supported by validated data and peer-reviewed methodologies. As the object continues its trajectory out of the solar system, opportunities for observation diminish. Its increasing distance reduces signal strength and observational resolution, limiting the ability to collect new data. This naturally shifts the focus toward analysis of existing datasets, which will continue to be studied and reinterpreted over time. In this sense, the object's passage becomes part of a longer-term scientific record rather than a single, isolated event. In the final section, we bring together the observational data, the interpretations, and the broader scientific context to understand what conclusions can and cannot be drawn from the available evidence. As 3I, Atlas, continues its journey beyond the planetary region of the solar system, the scientific community is left with a complete set of observations gathered over a limited but valuable window of time. These observations include imaging, spectroscopy, particle measurements, radio frequency analysis, and archival detections spanning multiple instruments and platforms. Taken together, the data provides a multifaceted view of the object's trajectory, composition, and interaction with its environment. In many respects, it behaves like an interstellar comet. It exhibits a coma, a tail, volatile outgassing, and orbital dynamics consistent with a hyperbolic path that will carry it out of the solar system permanently. At the same time, certain measurements differ from what is typically observed in comets formed within our solar system. Variations in volatile production ratios, elemental abundances, and isotopic signatures highlight the diversity that can exist among objects formed in different stellar environments. The radio observations that detected narrowband chirp-like signals remain an interesting data point within the broader dataset. While they were ultimately attributed to instrumental effects based on frequency alignment with known harmonics, their appearance in a specific observational configuration underscores the importance of careful signal classification in radio astronomy. No additional confirmed detections of similar signals have been reported, and no follow-up observations have identified repeating patterns that would suggest an external transmission source. The scientific process in cases like this is inherently iterative. Initial observations lead to hypotheses, which are tested against additional data, refined through analysis, and eventually formalized in peer-reviewed publications. Some findings are immediately conclusive, while others remain open to interpretation as more data becomes available. In the case of 3I, Atlas, multiple agencies and research teams have indicated that further analysis of the collected data will continue. Instruments such as MAGUS, UVS, SWI, and PEP generated datasets that require detailed processing and interpretation before final conclusions can be drawn. These analyses will likely be documented in future papers and technical reports. Archival preservation plays a central role in this process. By storing raw and processed data in accessible repositories, scientists ensure that future researchers can revisit the observations with improved tools, new models, and additional context. This is especially important for rare events like interstellar object encounters, where opportunities for new measurements are extremely limited.